Well, good morning. And again, I'd like to add my thanks to Doug and the team for putting this tremendous show together. I mean, the turnout has been fantastic. I've been to most Mines and Wines, and I think this one certainly takes the cake as the largest audience we had. I'll apologise in advance for my voice. Even though we were let out of the cave in Western Australia a while ago, I managed to find something on the way over. It's not COVID, by the way, but it certainly slowed me down and slowed my voice down. Some might say that's a good thing. So I'm going to talk about the Toongi rare metal and rare earth project. I'm going to give you some overviews of what I see as the scene, to set the scene in the global perspective. I mean, one of my pet hates is the rare earth and rare metal industry. I mean, these things are not rare. And I thank David for setting the scene too on some of the things that I was going to talk about, so now I can save my voice by not having to get into a detailed explanation of the structure of rare earth industry and the differentiation between the volumes of material, like much greater lanthanum, cerium content than there is of the key metals, the key economic minerals. But so I've just pulled up here a map put out by the USGS a few years ago now, just showing various deposits around the world, various types. But I'll just add that in 2011, the last time we had a rare earth boom, there were over 400 active rare earth projects in the world. I mean, these were all over the place, from amazing status, some of which I would have regarded as a geochemical anomaly, not a deposit, but that was the state of the market. Today, I think we've got about 150. If I leave out lithium, there's still a number of projects at various stages of exploration and development. And as I hope you'll see from this presentation, when I talk about what we've done at Toongi, the development of these projects is very much metallurgical process. Can you get the stuff out? Can you get it into a form that somebody's prepared to buy? And what does it cost? And those things are often governed by the host rock mineralogy, and I'm going to try and explain that. And then things like infrastructure, location become very important. I mean, I know I'm not going to denigrate the Canada here, but there's some nice Canadian deposits, but they're in unbelievable locations that, I've had the fortune to visit a couple of them, and when they're talking about the maximum temperature being minus 45 centigrade, and the minimum being minus 47 centigrade, you say, well, what's the difference? It's all cold, extremely cold. So that brings its other issues. So operating a rare metal, rare earth process, sorry, I'm saying that again, a non-rare earth, non-rare metal process just outside the city of Dubbo is not a bad option in my view. Important that fact at the bottom, China remains a dominant player, particularly in many of these metals and rare earths. So location. So the deposit's located about 25 km south of Dubbo. It was originally found by BMR, believe it or not, in 1951 as part of a radiometric survey. One of the lines happened to go right across the top of the deposit, and it gave quite a distinctive uranium, thorium, and potassium kick. And it turned out that they've used it for many years post that as a part of their calibration of their materials. And it was followed up by GeoPico in 1982 after the discovery at North Parkes, or Ganumbla, the real name. They looked at all volcanic alkaline intrusive rocks, and the geological survey demonstrated the location of these alkaline rocks just outside Dubbo, and went in and recognised it wasn't exactly the same as what they were looking at, but they drilled a few holes into it and came up with some odd niobium, yttrium and uranium results. And really, after that, sort of walked away, couldn't really see an economic value for those particular metals. We became aware of it in Alkane, and I'm using Alkane here. I've got to be careful. I mean, I've got an ASM hat on today, but basically my whole life has been in Alkane. We demerged ASM out of Alkane two years ago, about July 2020. Again, just to differentiate the copper, gold, and base metal business from the non-rare earth and non-rare metal business. So if I talk about we, I mean either Alkane or ASM. So we did based on a discovery that we'd made in a different organisation in the East Kimberley called Brockman, and David had it on one of his slides. We developed a very good understanding of process, of mineralogy, and more potentially the markets. What were the markets for these commodities going to be in the future? But we took that knowledge. When I was shown this project just outside Dubbo, I thought, wow, that's much better than 20 kilometres outside of Halls Creek in the East Kimberley. It's 25 k's outside a city of 40,000 people in a relatively civilised part of the world. So that's where we started, the start of the story. And we've embarked on that now over, it's 30 years, I think. So let's start focusing on some of the detail. The regional geology. So the deposit is part of an alkaline volcanic sequence or magma sequence it's been known in Eastern Australia for many years. There seems to be two time ages, the Permo-Triassic, Jurassic-Triassic age, and then a much younger, sort of more recent age of various different volcanic and intrusive complexes. So a name that Carl Spandler and Caitlin Morrison, I'll mention them more, but I'll acknowledge them in advance, did some tremendous work 6 or 7 years ago on the petrology, understanding and evolution of this deposit, and I think their work still stands out to me as the most seminal effort onto the project to date. And they named this area, they call it the TAMF. It's a Toongi alkaline magmatic field, and it's a very apt description because you've got multiple variations. So let's just focus in first. There's the Toongi deposit. We have one other, they call the Railway deposit, about 5 kilometres away, which is the only one of all of these orange deposits that you can see that carries elevated rare metals and rare earths. So it's all part of a volcanic and extrusive stage or evolution, and it's sort of, we'll come back to that at the end, and I'll try and explain what their views on how this originated. The deposit's been dated at about 190 million years, and you can see how it sits in what's almost like an embayment, which are Gunnedah sediments, Triassic and younger sediments coming in here, and the volcanics, the alkaline volcanics and intrusives, sort of sub-exposed throughout that whole sort of embayment area. That's what it looks like. Now, these are fairly simple cartoons, but it's better to have them like that. And there's the deposit itself. It's about 800 metres east-west, about 400, 500 metres north-south. The little black dots are RC drill holes, largely vertical holes, and then the white dots are diamond core holes. And they were drilled really just to compare the results we were getting out of RC, look more at the mineralogy, and then trying to relate that mineralogy ultimately to the extraction process that we were developing. And I think it's worthwhile noting that if you come down and look at the bottom graph here, so this is a sort of a composite cumulative graph of showing the grades, and you can see how virtually all the metals, zirconium, niobium, yttrium, that's cerium I think, is it? Yeah. Is an amazing non-variation. So we had a standard term internally that when we were drilling a hole, if we got results that were about more than 10% outside of what we believe was the average grade, we went back to the laboratory and said, "You made a mistake." And invariably they corrected us. So it's a remarkable deposit, but basically from east to west, from top to bottom, it's very similar grade. The grade has no variation. Underneath is a cross-section, a sort of an updated cross-section. We still don't know exactly what the dimensions are out on the eastern side, but what we do know is that somewhere between about 100 metres depth there, 130 metres, 150 metres depth out there, it's a very similar alkaline trachyte rock with this amazing metal distribution throughout it. This in fact is a model put together by Carl, and we have no reason to doubt it because that structure there we can see on aerial photographs, and it looks as though it links up to things like the railway 5 kilometres away. You'd describe these things as lopolithic or laccolithic, it depends on your point of view. One thing we're pretty sure about is that they were intruded or extruded into what were probably fairly soft sediments, and that boundary you can see there, that's the Napaby Formation. They were fairly soft sediments because the sediments have been pushed by the nose of the trachyte there into a form, and it's been silicified, which would certainly indicate there was a fair amount of water interaction with the host trachyte. The bottom, and I'll show you a little bit more about the bottom in a moment. Oops. So that's a cross-section through, a log section through TOD3, which is drilled virtually in the centre of the deposit. Now, while it's showing variations in the trachyte, they are really very much similar. There's not a lot of variation. You see, like you see here, vesicular material there. Sometimes it's more massive. But the best of our interpretation, our understanding, is it was really one body. It was extruded out, and I like to use the technical term lozenge, because that's what it looks like. There was this great lozenge of fairly viscous trachyte pushed out into what were felt relatively still soft sediments. I know it's going to be hard to see, but the bottom slide image here is the contact between the trachyte and that. I think it's there. Yep, out there, about 130 metres. And these are ferruginous, silty sediments, which look like a paleosol. And it was fairly indicative to us that there wasn't a lot of time difference between these sediments being deposited and then the trachyte being pushed out into it, for want of a better terminology. Getting down to the detail, petrology, you look at it, it's a very standard trachyte. The chemistry is very standard, peralkaline trachyte. The texture is very trachytic. You see the K-feldspar, some of which are partially sericitised, albite and aegirine, and they make up the dominant components of the rock. There's probably maybe 5%. We'll call them ore minerals for want of a better termination, but it also includes calcite and siderite, quartz, rhodochrosite, but not much. And the bulk of the other material are ore minerals. There's very little weathering. There's probably a skin on top of maybe 10 to 15 metres. The weathering not very much. It doesn't change much. The metal grades are virtually identical, and it's in a sense that it's remarkable in a deposit sense of what it is and what it would be to mine. Let's get into the ore minerals, because these are the most interesting and most important. So let's deal with zirconium first. And zirconium we call it a eudialyte group. It's not really eudialyte. Eudialyte, for definition's sake, is a sodium zirconium hydrous silicate. So it's not zircon. It's quite different to zircon. In our case, it's got different proportions to eudialyte. We've got not an overabundance, but an abundance of heavy rare earths and yttrium. Some small amounts of uranium in it as well. So it's not classical eudialyte, so we call it the eudialyte group. It's an easy way to try and describe it. And on the right, you'll see that image. These are very, very fine-grained minerals, and they're interspersed throughout the silicate material. And you can even see chunks of silicate material, and I'll come back to what that means further down the road, what Carl's interpreted them to mean. The niobium tantalum mineral, and I didn't mention much about tantalum at the front end, because basically while it's a very substantial tantalum resource, we've not yet been able to come up with an economic process to get the tantalum out. And I'll explain more about that when I show you the flow sheet. So again, we have a strange metal assemblage, or mineral assemblies, natroniobium, leucinite, that sort of thing. And these are sodium, niobium oxides or tantalum oxides with water as well, some thorium in the latter structure. The only thing that looks vaguely normal for those of us who work in the rare earth industry is that it's mostly in a calcium bastnasite, classic calcium rare earth carbonofluorite. Nothing much unusual about it. We have occasionally slightly enriched ones with strontium in them, but generally if you saw it, you'd say that, yeah, that's bastnasite. And the same sort of thing. Here they are over here, mixed up with a silicate assemblage. And probably the interesting thing, if you look back through all of these, is that they're very fine-grained. We're talking about things that are certainly sub 20 microns in size scattered throughout the rock. And that, again, is important when we come to look at the process that we've developed. So just showing the resource. So on the left-hand, the top rather, is the mineral resource. And the mineral resource basically covers all of that trachyte, the trachyte body that I showed you, the lopolith, you wanted to see it. And I won't go through the results, but you can see that it's a substantial resource of zirconium, hafnium, niobium, tantalum, yttrium, and then the rare earths. And I'm a scientist, I keep yttrium out, I don't add it into the rare earth content because it's not a rare earth, strictly speaking. And then further down we've got the reserves. Now the reserves are nowhere near as big as the resource, only because we said, well, really knowing the state of these markets, what happens, how dramatically they change, we can only justify at this point in time a 20-year life to the project. So we'll stick to a 20-year life. We'll develop a reserve around a 20-year open pit, and so that's why the reserves are constrained. I mean, strictly speaking, the reserves are going to be the same size as the resource because there is no grade variation. There's no grade control required. You basically go in and you dig up the whole of the trachyte. And we jokingly talk about the mine being very small, 1 million tonnes a year operation, probably half a dozen guys that pick in a shovel and a wheelbarrow. It's going to be the mining operation. The guts of it are in the processing plant, which I'll show in a moment. If you can see, if the image is clear enough, if you can see through it, in the background here, you can see that's that western edge of the trachyte. So that's that siliceous rim, probably 5 to 10 metres wide. It basically rims all the outside of the trachyte body, which I think, again, supported our view that the thing was intruded into relatively soft, liquid-bearing sediments. Now this I'm not going to take any credit for whatsoever. It's called passing the buck to Carl Spandler and Caitlin Morris, and I think it's a very sustainable model that I'm more than happy with when they presented it to us. But their view is that there's a large mafic, ultramafic intrusion below what is currently the TAMF today. Probably 10 kilometres. It's interpreted from regional gravity. There's a very distinctive gravity anomaly coming from the porphyry scene. You'd get quite excited by that. And their view was that the TAMF bodies formed during deep fractionation down in the magma chamber, which were extruded up. So these are the volcanic edifices that we see around the site with lava flows and tuffs and those sorts of things, and some intrusives. For whatever reason, and this is where it gets tricky, for whatever reason, there was part of that magma hung around, so it got caught in the subcrust and basically went unmixing to form immiscible blebs of rich in rare metals, and that silicate was basically what was extruded or intruded into that near surface environment as the Toongi deposit. And you can see a change in the character as you look at some of these things, the crystal structure. And what sort of gives it away, and I tried to allude it when we were looking at the images, is that the ore minerals, you can actually see where they've almost squeezed into a semi-crystalline igneous mass, being the trachyte itself. You can see chunks of other crystalline bodies caught up within them. So, yeah, I mean, I'm not prepared to argue with anybody. This to me is a fairly reasonable model. And then you can take this model and you can apply it anywhere else in Eastern Australia if you wish. And I said the flow sheet, which really is the, I don't use the terminology, the guts of the project. It's great having the world's biggest and highest grade and whatever, but unless you can get the stuff out, and reasonably get it out into a form that's saleable at a cost, a reasonable cost. So simplistically, you go back to those diagrams I showed you of the ore mineralogy. They're all very fine grained, sub 20 microns. There was no way we could produce a mineral concentrate. We can't float it, you can't do other physical separations. So we were faced with a whole of ore solution, and that's basically what we've done. This was done in conjunction with, in the latter years, with ANSTO at Lucas Heights. But basically it's a whole of ore sulfuric acid leach. So what happens, we get the rock, we crush it up, we grind it, and then we mix it with sulfuric acid, and we heat it up in a kiln, and then mix that with water, and then that comes out, and we recover, we separate out the solid liquid, we do a solid liquid separation down here, and then those liquids go off to do various separations. And they go through a solvent extraction, the first solvent extraction phase, which separates out the zirconium hafnium from mostly the light rare earths and the niobium. The niobium comes out as a separate stream, the zirconium comes across as another separate stream, and I'll come back to the other things there. And then the rare earths go down, and will produce a series of separate rare earth products. And I'll come back, if I go back to the top first and look at so we'll produce zirconia and zirconium chemicals. And by zirconium chemicals, I mean one of the major market products for zirconium material today is zirconium oxychloride. And you've probably never heard of it before, but it has widespread applications across industry. Hafnium, and I didn't really mention a lot about hafnium front end because people tell me I talk about hafnium too much. So basically, zirconium and hafnium are chemically very similar. They're actually very hard to separate, and we pay acknowledgement to ANSTO, the ANSTO team, when we said we've been asked by our market can we produce a separated hafnium product, and you'll see at the end the applications as to what we can do. And to be fair, within 6 months, they came up with a flow sheet that separated hafnium, which basically we've patented, so it's a patented process. And there are very few others globally that can do this, can do it effectively. So we've now got a very good flow sheet that produces, not only does it produce zirconium products, but it produces hafnium products. And on the market sense, because the hafnium market currently is quite finite, we only take part of that stream to come out and produce the hafnium material. What have I done with that? That's the hafnium material there. So yeah, we produce dehafniated zirconia. Again, there is a market for dehafniated zirconia. It's an interesting market because the moment you dehafniate zirconia and try and transport it, because of the association with the nuclear industry, you have to get special dispensation to transport dehafniated zirconia. The reason being, dehafniated zirconia mainly gets used in the nuclear industry for making the reactor vessel, the tubing that holds the nuclear fuel in place, so it's a very important material. On the other hand, hafnia is used for control rods in nuclear reactors. So there is an important differentiation. And you do get into some interesting global conversations. Niobium, the niobium market is very, very much dominated by ferroniobium. It goes into the steel industry and does all sorts of things. So it's pretty straightforward. And then down to the rare earths, and David set the scene on this quite a lot. So, we'll produce a niobium praseodymium oxide, and I'll explain why in a moment. We produce separated terbium oxide, separated dysprosium oxide, which is the key value components. If you look at the whole revenue stream built into that, about 40% of the revenue stream comes out of that. And another 30% probably comes out of that, and then something like 10 there and another 20 there. So it's an interesting mix, but in terms of right now, with these amazing rare earth prices we're seeing again, that probably produces 40% of the revenue stream. Things like samarium, europium, gadolinium we'll sell as a chloride concentrate to other producers or consumers around the world. Yttrium heavy rare earths will go as another separate concentrate. It's disappointing by the yttrium because it's a fairly big volume for us, and when we started this phase of the project probably 5 or 6 years ago, it had substantial value. That's dropped away dramatically because of the change in phosphors. The change from LCD type phosphors and lighting into televisions to LEDs has dropped the demand of yttrium quite dramatically. And again, I'll comment here that in these commodities, you've got to always be very, very careful of the future. Where will the future be for some of these metals in 10 years' time or 20 years' time? If you're going to build a $1.5 billion processing plant, you want to be pretty sure you've got at least 20 years. The other thing I will mention, again, is over here. It says lanthanum and cerium goes to waste. Really, the amount, even though it's quite large volumes of lanthanum and cerium, there is no merit for us to actually try and recover it and separate and transport. The cost of transport outweighs the value of the raw material. This is a snapshot. When you get into these metals and these commodities generally, it's very hard to summarise in a short space of time the applications. But things like zirconia, I mentioned nuclear zirconia, thermal barrier coatings. They put them on turbine blades to stop, in jets, to stop the aircraft picking up dust in the atmosphere, volcanic dust, and fusing the turbine blades and basically making the engine stop. So that's important. It's important both in passenger jets and in military jets. Ceramics, an enormous amount of zirconium goes into ceramics, refractories, solid oxide fuel cells. If you start looking at the hydrogen market, you'll find that a lot of hydrogen fuel cells have a zirconia ceramic basic driver. Lots of chemicals, other fibre optic cables. And hafnium. And hafnium is one of its big uses outside of the nuclear industry, is for things like superalloys, aerospace alloys. It's a very high temperature metal. It can resist amazing temperature. I think the current world record for a man-made product is something like 4,500 degrees centigrade, and it's a hafnium nitride, for what that's worth. But it means there's just a lot of applications and discussions going on. Plasma cutting tips, this little thing over here is a plasma cutting arc. An amazing amount of hafnium gets consumed in that. The ones that are probably most exciting applications in semiconductors, like ferroelectric data storage systems and thermoelectric applications. And again, I don't have time to bore you with all of that, but needless to say, the hafnium market, which today is about probably 70 tonnes per annum, big market. Basically, we believe, talking to the downstream consumers, is that somewhere over the next 4 to 5 years, that will probably go up close to 200 tonnes or even 300 tonnes at demand. It's a very interesting metal. Niobium, mentioned its main applications is in low alloy, high strength steels, which is where niobium mostly goes. But there are other things like superalloys and those things, superconductors. Then the rare earths. I'm sure you've probably heard enough about rare earths in the last 12 months, but the big demand is still the FEMB permanent magnets. And what I should have said, but I'll still, hang on, let's go back. I should have said that here. Yesterday, ASM announced that its metal plant in Korea is actually now in commercial production. Just a quick explanation about that. 4 years ago, we tied up with Chungnam National University and their materials science group, who developed a new kind of metallisation process. And initially it was designed for zirconium production, zirconium metal production, for the Korean nuclear industry, but they also found it could do other things. So we've been applying it to our zirconium product, our hafnium product, but in the last 6 months, into neodymium, praseodymium, terbium and dysprosium. And one of the key products that we'll produce is what's called a neodymium praseodymium strip metal. That material goes straight into the manufacture of NdFeB magnets. ASM will become one of the few Western companies producing a metallised strip metal which is enabled to go straight into magnet production. It's worth knowing. There's a lot of time and energy that's gone into that. So that's sort of where I think I'll sign off on where it's at. And again, I just like to restate, the effort. I mean, I stand up here talking about it, but there's a lot of people behind this scene that have put time and effort into the whole ANSTO team, the whole team inside Alkane before it demerged to get it to where it is today. And then the odd academic study like Carl Spandler and Caitlin Morris, which I still today was probably one of the first time we could stand up and talk publicly about how this deposit formed. Thank you.